Right now, over 10,000 aircraft are flying simultaneously worldwide, separated by as little as 1,000 vertical feet and miles horizontally, yet they never collide. A single transatlantic flight chooses from millions of possible routes, optimized in real time for fuel efficiency, weather avoidance, and air traffic flow. Here's the invisible AI coordination system managing the world's most complex transportation network, where algorithms save airlines $40,000 per flight, and a single routing mistake could waste 10,000 pounds of fuel. Every commercial flight represents a complex optimization problem involving thousands of variables: wind patterns, air traffic congestion, weather systems, fuel costs, aircraft performance characteristics, airspace restrictions, and arrival time requirements. Finding the optimal route through this multidimensional problem space requires sophisticated algorithms that process vast data in real time. A typical transatlantic flight from New York to London could theoretically follow millions of different paths. Modern flight planning systems evaluate thousands of these possibilities within seconds, selecting routes that can save airlines $40,000 per flight through optimized fuel consumption, reduced flight time, and efficient traffic flow integration. Aircraft don't fly random paths across the sky. They follow structured highway systems in three-dimensional space. The global airspace contains thousands of designated airways, invisible highways in the sky defined by waypoints, specific geographic coordinates. These airways form a structured network similar to interstate highway systems, enabling predictable traffic flow and standardized routing. Airways connect waypoints with alphanumeric identifiers like NORS, MUSAC, SHINY placed at strategic locations. Aircraft navigation systems guide planes from waypoint to waypoint, creating efficient routes while maintaining separation from other traffic. Airspace is divided into altitude layers typically separated by 1,000 feet above 29,000 feet FL290. Eastbound flights use odd altitudes, FL310, FL330, FL350, while westbound use even altitudes, FL320, FL340, FL360, creating vertical separation that prevents head-on conflicts. High-altitude winds dramatically affect flight efficiency, with jet streams offering 200+ mph tailwinds or headwinds. Eastbound transatlantic flights actively seek jet stream cores, gaining 200 mph tailwinds that can reduce flight time by 30 to 60 minutes. Westbound flights avoid jet streams, sometimes flying hundreds of miles off the shortest path to minimize headwind penalties. North Atlantic routes change daily based on jet stream positions. Airlines submit preferred routes considering forecast winds, with air traffic control coordinating to optimize traffic flow while accommodating individual flight preferences. A 100 mph tailwind can save 5,000 pounds of fuel on transatlantic flights, worth $15,000 to $30,000 at typical fuel prices. Route optimization algorithms automatically calculate wind-optimized paths that may be geographically longer but temporally and economically shorter. Modern aircraft continuously receive updated wind forecasts during flight, enabling pilots to request route modifications that capitalize on favorable winds or avoid deteriorating conditions. Thunderstorms, turbulence, and severe weather require dynamic route adjustments. Aircraft weather radar provides real-time precipitation and turbulence detection up to 300 miles ahead, enabling proactive weather avoidance. This data integrates with navigation systems suggesting deviation routes around severe weather. Air traffic control issues, significant meteorological information, SIGMETs identifying severe weather areas. Route planning systems automatically avoid these regions, suggesting alternative paths that maintain schedule while ensuring passenger comfort and safety. Advanced algorithms predict clear air turbulence using atmospheric models, wind shear data, and pilot reports. Airlines route flights to avoid forecast turbulence areas, improving passenger comfort and reducing aircraft structural stress. When widespread severe weather affects major traffic corridors, air traffic control implements strategic routing initiatives redirecting multiple flights around weather systems, requiring complex coordination to maintain safe separation. With 10,000+ simultaneous flights, sophisticated systems prevent mid-air collisions. Traffic collision avoidance systems use transponder broadcasts to track nearby aircraft positions, speeds, and altitudes. When collision risk develops, TCAS issues resolution advisories commanding immediate altitude changes, climb or descend, that coordinate between aircraft to ensure diverging flight paths. Air traffic control maintains minimum separation, typically 5 miles horizontal or 1,000 feet vertical in controlled airspace. Sophisticated algorithms predict aircraft positions minutes ahead, ensuring separation standards remain satisfied despite speed and direction variations. Over oceans where radar coverage doesn't exist, aircraft maintain larger separations, typically 50 to 60 miles lateral, 1,000 feet vertical, using GPS navigation. Modern satellite-based surveillance enables reduced oceanic separations, increasing airspace capacity. Major airports and airspace sectors have capacity limits. Flow management algorithms assign departure times, slots, ensuring traffic demand doesn't exceed airspace or airport capacity, preventing dangerous congestion. Airlines program cost index values balancing time costs against fuel costs. Low-cost index prioritizes fuel economy over speed, using slower cruise speeds that burn less fuel. High-cost index prioritizes schedule over fuel costs, using faster speeds that complete flights quicker despite burning more fuel. Modern flight management computers continuously recalculate optimal cruise speeds considering current winds, remaining distance, and programmed cost index, automatically adjusting thrust to maintain economic efficiency. Low-cost carriers typically use low-cost indices maximizing fuel efficiency, while premium carriers use higher indices prioritizing schedule reliability and passenger experience over fuel costs. Cost indices consider current fuel prices, aircraft lease costs, crew costs, and passenger connection values, creating complex economic optimization that varies by flight, route, and market conditions. Busy airports require sophisticated arrival management. Standard terminal arrival route stars are pre-planned descent paths guiding aircraft from cruise altitude to approach. These procedures optimize traffic flow while managing noise abatement and terrain avoidance. When airport arrival demand exceeds capacity, air traffic control assigns arrival times, creating spacing that prevents excessive holding patterns. Algorithms optimize these assignments, minimizing total delay across all flights. Modern arrivals use continuous descent approaches, CDAs, maintaining constant descent from cruise to landing rather than level flight segments. CDAs reduce fuel consumption 20 to 30% during descent while significantly reducing noise. Major airports use slot systems allocating specific arrival and departure times. Airlines compete for desirable slots, with optimization algorithms helping airlines select schedules maximizing network profitability. Next-generation air traffic management incorporates advanced technologies. Future systems will manage flight paths in 4 dimensions, minus latitude, longitude, altitude, and time, enabling precise spacing that maximizes airspace capacity while maintaining safety. Machine learning algorithms will predict traffic patterns, weather impacts, and optimization opportunities, automatically suggesting route improvements that individual pilots and controllers couldn't identify. Future airspace won't use fixed airways but dynamic routing that adapts in real time to traffic demand, weather conditions, and special events, maximizing efficiency and capacity. Distributed ledger technology may enable direct aircraft-to-aircraft coordination with verified safety and efficiency, reducing dependence on centralized air traffic control while maintaining coordination. Flight route optimization represents one of humanity's most sophisticated logistical achievements. A system coordinating 100,000-plus daily flights across interconnected global networks, optimizing billions of dollars in operational costs while maintaining perfect safety records through algorithmic precision and human oversight. Every flight demonstrates invisible coordination, managing complexity that exceeds most computer networks, traffic systems, or logistics operations. The sky contains a 3-dimensional highway network carrying more passengers annually than all other transportation modes combined, operating with reliability and efficiency that makes routine what should be impossible. The next time you track a flight path on your phone, remember that curved route represents algorithmic optimization considering hundreds of variables, coordinated with thousands of other flights, all managed by systems processing millions of data points to ensure safe, efficient travel.